So happy Monday morning, everyone. Does anyone have any questions about assignment 1?
Lots of questions, not only one. I try to understand IBM Watson and Rugby.
Okay.
I obtained a kind of visualization, but I'm not sure that it is correct answer. I think it's not complex because I just use only two properties, only two values to compare. I think we need to show us or Richard to be sure it's true or not.
Yes, definitely. You are welcome to show me anything before the deadline, and I can give you feedback. That's perfectly fine. And I'll tell you, like, if you want, you can even write up the summary, and I'll tell you if you'll get all the points or not. It's fine. So you can ask any questions. You could come to me with the completed assignments before the deadline and say, are there any points missing? And I would tell you if there are any points missing, for example. Yep. Someone else asked if they could use data that wasn't in the Public Health England website, so include additional data. That is definitely okay. This student, I meant to print it out and read it off, but somehow I didn't manage. But they wanted to include the locations, I believe, of power plants in the UK to see if there was any relationship between some of the health problems and the locations of power plants, and maybe some additional map data. I think they were thinking about some additional map data. But everybody noticed there is a map of all the CCGs on the Public Health England web page that you're welcome to use. So, but there are lots of map data, and you can download that in the assignment. There's a link that says, like, here's a lot of map data if you want to download it. But it's not really, I think that the most interesting map data for this is the CCG map that you see there. Any other questions? I can feel the anticipation about assignment 1. It's so exciting. Wait until you see assignment 2. You can have a look at assignment 2, by the way. There's a copy of last year's assignment 2 on Blackboard, as far as I know. Okay, good. Let's start then. So we were talking about some very exciting topics last time. And we were talking about graphs, and then, so here's just a refresh of our memory, right? Graph optimizations and challenges, the London graph, which is manually drawn, right? And then algorithms, automatic algorithms for graphs, and different examples. And then we just went into some fun example about some fun ideas, right? How we can interact with graphs and animate them and add curved edges, and a little bit about a system that has these features built in. And you can, this is a little video of that visualization system, and there's a copy of this video on my webpage and on the DataVis YouTube channel. And now we're going to talk about n-dimensional data. This is a little bit confusing, the terminology, because we can refer to n-dimensional data, multivariate data, and high-dimensional data roughly similarly the same thing. They're often used interchangeably. some people use the term multivariate data to mean some number of dimensions like 5 or fewer, and then some people use the term high dimensional data to mean some number higher, maybe 6 and higher. N-dimensional data is a nice term that covers all of those. So this is a great example of a higher, well, this one's 3 dimensions, I believe. So this is a scatter plot, right? I think everybody's seen this before, and you can use this in assignment 1, right? There's a variable on the x-axis, the minimum and maximum values plotted against another variable on the y-axis. And then a third variable can be plotted to color, right? And here you can see there's a direct relationship between weight and size, which is not very shocking, is it? I believe that's for some cars in this case. And I'm not sure what the color is mapped to in this case. Can anybody think of a way to add another variable to this? A fourth? Who said that? Say your name again?
Wong.
Wong. Yes! So, Wong said you can change the size of these ellipses, that's adding another variant. And is there another way? So that's that. We added size, that would be 4. Could we do anything else? Could we add 5? So something else?
3D.
3D? Yeah, you could add a third dimension, a depth, and get 5 variables. Well done. Somebody got a good night's sleep. Any other ideas? Could we go to 6? Who said that? What's your name? Lee. Yes, you could change the shape of those and encode another variable.
Quantity, amount.
Excuse me?
Quantity or amount.
Well, the shape of these, for example, imagine this was a triangle or a square or a 5-sided polygon, 6-sided polygon, for example. Any others? Any other ways? Could we add another one? I've lost track. I think that was 6. Is there another thing we could add? The answer is yes. Otherwise, I wouldn't be asking. So we could animate it, and that would be an added dimension. And there's another one which would be, there are 2 more that would be very difficult to guess. Transparency, you could vary the transparency of these. And texturing, texture mapping could be used as well. Those are not perfect examples, but just to get your mind thinking in this direction, right? But you have seen in the graph example, the animation and the texturing. Here's yet another way. This is called the Scatterplot matrix. So imagine we have 3 dimensions. Right? In this case, we have retail price, average size, and horsepower. This is again a description of cars. And we plot each one of those against the other. So here it's retail price against retail price against average size, and retail price against horsepower. And then we do the same thing on in the other direction, retail price against average size, retail price against horsepower. And by having a matrix like this, we cover every combination. Right, so this is an example of an n-dimensional visualization. In this case, n is 3, so it's not very exciting. But it works. Right? You can notice some things that are not very exciting, right? But this is not very exciting. Retail price against retail price, and average size against average size, and so on. The other thing to notice is there's some redundancy, right? We have average size against retail price twice, right? So we have, oh, this is horsepower against retail price. This is also horsepower against retail price, but it's flipped by 90 degrees, so there's some redundancy in there. But you could take any number of dimensions theoretically and plot them on a scatterplot matrix. Right? Anybody see any limitations with that? Like, say your name. What's your name? You don't want to say your name? That's the first time anybody's ever done that. Yeah, so you run out of space.
Yeah.
Right? If you have 10 dimensions, you have a 10 by 10 scatterplot matrix, you can run out of space, right? So it doesn't scale very well. This is a scatterplot matrix but with interaction. So you can click on the different data items, right? This is a focus and context visualization. Somebody has clicked on one of the data items, it's become the focus of the visualization, and then the rest has been grayscaled out, right? And this one is the Honda Insight, right? Which is a hybrid gas electric, or here you would say petrol electric car, right? Somehow, look, it's sticking out. It's a special car, right? Here's this car, and here are all the other cars. So something is very special about that car, right? So the user wanted to find out what was so special, and they clicked on it. And they got this information, right? It's got 66 miles per gallon on the highway, and it has this much weight, and so on. So that's adding interaction. This is an example of a 3D scatter plot, like we mentioned, that we could add a third dimension and get 3 views at the same time. You can see there are perceptual challenges here. It's hard to discern the depth information. It's difficult to just see it, right? There's no shading. There should be at least some shading on the ellipsis, and then you could rotate the volume, and that will help you discern the depth. Right. Here's a stacked bar chart example. So we have different, in this example we have different universities, right? Each bar is a university. And then each color is a subject that they're teaching, right? So, and this is trying to visualize the state of higher education in Wales, by the way. This is a real problem. There are people at Swansea University trying to understand what skills in education that Wales is delivering, right? So there's a workforce, right, and they want skills. They're hoping to get skills from higher education, and then there's a higher education, and they're delivering skills. And the question is, do they have any correspondence? So that's the idea, right? And we can add different mapping options, right? We can map the columns to subjects, we can map color to something else, and size to something else, and so on. Right? And the thing that sticks out, what sticks out? Does anything stick out on this visualization to anyone? It must be a sleepy Monday morning. Nobody notices. There's a bar missing.
Yeah, Royal.
The Royal Welsh College of Music and Drama. Anybody heard of that? Well, that's just not teaching these chosen subjects. So they're just not teaching like law and social studies and so on. So they show up as an empty bar, which isn't very fair. You can also notice some other things. For example, like University of Wales, Cardiff has quite a big business activity. And so does Morgan, University of Morgan, and so on. So it's a useful visualization. Right? So you can see lots of different trends there. And find out what's happening in Wales. This is a stacked graph showing similar information. Each color represents a subject, and then we have along the x-axis the different universities again, right? And that actually tries to show the same information, right? But it doesn't make as efficient use of space. This might make a little bit more. This might be a better choice. It's still a good choice, and it's still good for assignment 1. This might be a good choice too if this was time on the x-axis, for example. By the way, on the y-axis is the number of students that study those subjects. That's the y-axis in this case. That's good for, all of these are good for assignment 1, by the way. This is a matrix chart. It's kind of similar to the scatterplot, actually. It's not that different from a scatterplot. Right, we have the universities along the x-axis, and then the number of students along the y-axis in some ways. Well, no, the category of students on the y-axis. So this is undergraduate students, and this is postgraduate students. And then the number of them is mapped to the radius of the ellipse. Right? So Swansea University is currently trying to increase its number of postgraduate students, right? Which I'm sure that the College of Science has done since this graphic was made. So those are some n-dimensional visualizations, some very common ones. And we're going to continue on with n-dimensional visualizations. But this time it's a special class of visualizations called Glyphs, which you've all seen before, actually. Anybody know where you've seen Glyphs before?
Rugby.
That's right. We showed them in this module. Did you see them outside this module ever, in real life, so to speak? Has anyone here seen a glyph in real life? Where's the attendance? Is it still going around? Lucky you guys. Casey, have you seen a glyph in real life, do you think? Never? How about, has anybody ever been in a car? A car. Yeah, you've been in a car before? You see, like, road signs. Road signs use glyphs.
Yeah.
Right? That's a very common example. Or maybe you're walking around campus and you see, like, there's been some construction work and there's a do not enter glyph, or some, like, this is a wet floor glyph, like danger, Will Robinson. So let's talk a little bit about glyphs. These are famous glyphs. I don't know if these are really a scientific experiment or if they're like a joke. I've heard both ideas, but they're very famous nonetheless. Right? They're called Chernoff bases, and they're a glyph that encodes several variables. Right? So each glyph has an x coordinate, an x position, and a y position, just like a scatter plot, right? But then those are the first two variables, right? Then there are other variables encoded in the head, the shape of the head. You'll notice there are different shapes, right? Some are like potatoes, Mr. Potato Head. You guys see that over here, Mr. Potato Head? Has anybody played with that before? You guys are missing out. The mouth encodes variables, right? There are different shaped mouths. I guess these are just like your mobile phones now, right? You never thought of encoding data. Well, some data with your mobile phones. The eyes have different shapes, right? Some eyes are big, some eyes are small. So you can encode lots of different variables in these shapes, right? Head curvature, mouth length and curvature, nose length and curvature, eyes, shape and size, color, XY position. And if you look at the original paper, it's used to encode 8 different variables of fossil specimens. That's the original paper from 1973. It's they're quite famous. So we mentioned them. Here's another example of high-dimensional data. So in this case, we have these things called star glyphs, and there's 1, 2, 3, 4, 5, 6, 7, 8 different axes. And they're all encoding something. So we have an 8-dimensional visualization there. I haven't told you what they're encoding and how they're encoding it, but we're going to talk about that today. Here are some vector glyphs. So these encode direction and magnitude, right? That's an arrow glyph, right? So in this case, it's visualizing fluid flow, right? There are 7 variables visualized: the x, y, and z position, right? There's an x, y, and there's a depth position, right? There's a velocity which has 3 components: an x component, a y component, and a z component, and there's magnitude, right? How is magnitude depicted in this visualization?
Speed of flow.
That's right. How is it reflected in this visualization? How is the speed of the flow reflected?
Size of arrow.
Nice. What's your name again?
Rishita.
Rishita. Okay, very good, very good. The size of the arrow encodes the speed of the flow. Right. And the color. So the color, we could have 8 variables if we wanted to. Range glyphs are another style of flow visualization glyph. This is a theta range glyph, right? So each region of space here represents a number of velocities, or a range of velocities, right? So how do we encode the range? We have an x along the x-axis. We have the primary direction of the flow here, but then we have a range of varying angle, or theta angle, which we encode by theta, inside this region. So the greater the theta is, the more variance we have in the direction of the flow, right? And that's how we map that information. Right? So there are eight variables visualized there. We've added the angle range onto the glyph. Here's one for just the magnitude, to visualize the variation in magnitude. So again, each area represents a collection of flow velocities, right? And then the minimum magnitude is mapped to the minimum radius, and the maximum magnitude is mapped to the maximum radius for this region, right? And that's called a range glyph, right? So we have 6 variates visualized, position, x, y, and z digits, the velocity range, and the magnitude. Does that make sense, hopefully? It's good to know that catering services is working very, very hard. And these are hybrid glyphs, right? So they have the vector in the middle, and then they have the range on the outside, right? So we can see, for example, that the magnitude here doesn't vary at all in this region, but the magnitude of velocities in this region varies quite a lot. So here's more or less uniform flow, and here is highly variable flow. Right, so there are 9 variates being visualized at position, velocity, velocity range, and magnitude. It's a lot of information to be encoded in a single glyph. Here's another one. Anybody here watch Rugby? I have extra copies of the lecture. Does anybody want an extra copy? You could just pass those around. I know there are some Welsh people that watch Rugby here. So this is a glyph that encodes a lot of information about rugby and rugby games. I think most of us know that during a professional match of rugby or football or basketball or any professional sport, there are people sitting on the sidelines and recording information about all the events that happen. Right, they're already doing this and they're storing it in a database, basically for entertainment purposes, right? So this glyph happens to be for rugby, and each glyph represents one event in a rugby game. So these are the properties that it represents. The time at which the event happens. So if the midnight position is the beginning of the game, this happens shortly after the beginning. The thickness of this red arrow is the duration of the event, how long it lasted. Right? There's a curve here that represents tortuosity. Tortuosity is mapped to curvature. Has anybody heard that word before? That's probably a word that nobody's ever heard of before in this room. Has anybody heard of tortuosity? So it describes how much the player ran in a curved fashion, how curved the path was that they ran in. Right? So you can there's a ratio of just a straight line from start to end over the curvature, and that's called the tortuosity.
So it is applicable for the other games like football, hockey, and...
That's right. In theory, you want to have a straight line, right, from the defensive position into the goal. So that's the theory, right, or that's the ideal case. And the amount of tortuosity is the zigzag that the player actually went in to go downfield. Territory start position is mapped to radius. The contour color is mapped to team, which team is the team identifier, and then the net lateral movement is indicated with an arrow glyph. N is the number of phases. The direction of the ball movement is indicated with this arrow orientation, right? The start event or the type of event is shown using a pictogram, and then gain is mapped to the inner color. So let's see some examples. By the way, gain is the amount of territory that's towards the goal. Right? So this is what gain looks like as it changes, right? gain, negative gain, meaning going backwards, is red. Marginal gain is dark green, and so on. Major gain, so that's what the gain looks like. These are the different events: kick receptions, lineouts, turnovers, scrums, and penalties. This is what it looks like when we vary the territory start position, right? So this is the defensive territory, and this is the attacking territory, right? Mapped to this radius, and then tortuosity as it increases, right? This is actually the representation of a straight line in the game. The number of phases, right, is just mapped to this symbol. The direction of the event is mapped, right, backward direction, and so on to forward direction. The net lateral movement is mapped to the width of this arrow, right? And then the time is changing, and the phase duration is changing. So all that information is encoded in this one glyph. It's a lot of information, right, for each event. And then we can visualize a rugby game using these glyphs. So that's an entire rugby game in a single scatter plot. Every event in a rugby game. So we can get through the rugby games very quickly. Right? The traditional way for a coach or a trainer to build a strategy, maybe design a strategy to beat some opponent, is to watch the game, right, from start to finish with a DVD player or a video cassette or something like that. But that's very time consuming. Right? So it would be nice if we could accelerate that process. And here we could see the whole game in just a few seconds, right, on a scatter plot. This is the x-axis encodes time, and in this case, the y-axis encodes gain, right? So we can see the events with the high gain immediately. These purple halos signify scoring events or tries, right, in rugby. So that's the scatter plot. This is the glyph panel control that we can use to interact with the glyphs. And we can compare matches with one another, right? Here we'll show a little demo of that. And you can find this also on the DataVis YouTube channel. This is an alternative way to watch a rugby game, or to analyze. Really, this is to analyze rugby games. Right? So we can sort the glyphs by any attribute that we choose. Right? We can sort them by start time, event time, but we can also sort them by, for example, the event, the type of event, or some other attribute. Right? So this is sorting the glyphs by the type of event. And we can see immediately, for example, all the tries are associated with lineouts. Just within a few seconds, we can make that observation. So somehow, in that game, lineouts were a very successful kind of event. Right? And we can see that kick receptions are usually associated with low gain, for example, on those kick receptions. We can compare territory start position with the number of phases by clicking on the territory start position and the number of phases in the glyph. So now we can see that the tries, or the scores, are associated with higher phase numbers, which is not very surprising, right? We can select glyphs for focus and context rendering, right? These are the focus glyphs, and these are the context glyphs. And we can sort by tortuosity. We can see that tortuosity increases, right? And we can do multiple sortings on the glyphs. We don't have to sort them just by the two axes, but we can sort them 3 times, right? We can expand the x-axis and then sort all the lineouts again, right? So that's the idea. So we can analyze rugby games interactively with glyphs, and we can make observations that would be very difficult, if not impossible, to make the traditional way just by watching the game in the traditional way. And you're welcome to have a look at that video, at the online version. Okay, and the next, so that's the end of the glyphs part. Right, we're still on n-dimensional data or high-dimensional data. Are there any questions about the rugby glyphs or rugby games? I'm definitely not a rugby expert. We'll start with the parallel coordinates. These are the tenets. So parallel coordinates are another high-dimensional data visualization technique, and this is what they look like. So for every data attribute, we have an axis, and each axis has a minimum and maximum value. Right? So here we have the percentage of plain text. This is for document visualization. And here we have the number of pictures, the number of figures in a document, the percentage of time people spent looking at page 1, the percentage of time the number of times people spent looking at the conclusion of a document, and so on. And then each person is represented by a polyline. So this person spent this percentage of time looking at plain text. They spent this percentage of time looking at a picture, this percentage of time looking at figures, this percentage of time looking at page 1, and so on. You can see I'm having trouble following the line, actually. So how does that work? How is that useful? I'm going to try to explain that right now. If I can find the eraser. Wake up. Markers. So imagine we have 2 variables, x and y, and we want to see if there's some sort of a relationship between x and y. Right? This is right. We want to visualize, now normally we might visualize x and y with a scatterplot, right? A Cartesian plot is another way to say that, right? right? So how would we do this normally? We would put x on the x-axis and y on the y-axis, so to speak, the horizontal axis and the vertical axis, and we would do this. We'd go 1, 2, 3, 4. We'd move over 4 positions and then up 4 positions. 1, 2, 3, 4. Right, and then we plot the intersection. Right. For 9 and 3, we would move over 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we would move up 3 to 1, 2, 3. 10 and 2, and then we would do the same with the other numbers, right? 10 and 2, 11 and 1, right? 10 and 3 again. So this is 11 and 1, 10 and 3, 1, 2, 3. So everybody knows how to make a scatter plot. But we were talking earlier about scatter plots. What happens if we want to add a third dimension? Right, we could add color maybe. If we want to add a fourth dimension, we could try to add depth. But it quickly runs out and it gets very confusing. Is there an alternative way to visualize that same data or n-dimensional data that's a little bit more, that lends itself to an easier, higher dimensional visualization? So imagine now just taking the x-axis and flipping it 90 degrees. So we have x here and y here, right? This is the minimum x and the minimum y now, and this is the maximum x and maximum y. And here we mark the zero axis, or the 0 point of 0 value. And x, so now when we plot x is 4, 1, 2, 1, 2, 3, 4. The position 4 on the x-axis is there. Same as here, 1, 2, 3, 4, right? And 4 on the y-axis is here, 1, 2, 3, 4. And to show that they're connected to each other, we just draw an edge between them. Like that. So this point, 4, 4, is now an edge in parallel coordinates. Right? And the advantage there is we can now add as many axes, well, we can add lots more axes if we want to. Right? So if z is -4, for example, we would go down 4 units, 1, 2, 3, 4. Right? Looks like my marker is getting dry. Right? And we can keep going. We can have -3, right? That's the z-axis, by the way. We can add another axis, and this is the alpha axis, and we want to plot -3, which is 1, 2, 3, right? And we can add a beta axis. Keep going. So in this case, we have 1, 2, 3, 4, 5. So we can visualize n-dimensional data in that way. Did that make sense? Hopefully. So you all.
For the two-dimensional data, we can plot as normal Cartesian plot.
It's Cartesian coordinates,
Cartesian
yep.
plot, and for the multi-dimensional data, we can use the parallel one.
Correct, yep. So does anybody remember that email I read a week or two ago that said, is there a way to visualize 10-dimensional data for arbitrary attributes? Now you know the answer. Here is the answer. Using parallel coordinates. So that's what that looks like. This is, oh, I should probably turn on the display again. This is what it looks like when you add color to the polylines. So you can select polylines, for example, and interact with the visualization, but you can also apply a color map, right, to facilitate tracking of the polylines, right, across the different axes. And so I guess we'll stop there and continue on at this point on Thursday. Happy Monday morning.